have calculated limits by doing tables and by looking at graphs. So now I want to use these limit laws to calculate it. The first few problems on your homework are going to look like this example where it says to justify everything with a limit law. I am not going to make you do that. Like, I don't want you to do a step and tell me that's law number 1 or law number 2. But what I'm going to ask on these is that we kind of show what we're doing. So I don't just want a final answer. I want to rewrite this so that we can use our limit laws. Okay? So we had a law yesterday that said if you have things added or subtracted, then you can do the limit of each one individually. And we also said that if you have a constant, you can write that constant in front of the limit. So in this example, I can do the limit of each of these separately, and this coefficient can come out in front. So I can write this as 2 times the limit as x approaches 5 of x squared minus 3 times the limit as x approaches 5 of x plus the limit as x approaches 5 of 4. So I realize this is annoying, writing the limit as x approaches 5 3 times. We need to do it right now. That's our work. We'll get to the point where we can talk about when you have to have it, when you can leave that off. But for now, we need it. Okay. So, for evaluating these things, instead of making a table of values, we had these rules. So if you take a quick glance back at your rules, said you have the limit of x to a power. It's just a, what your limit was approaching, to that power. So the limit as x approaches 5 of x squared is just going to turn into 5 squared. Minus 3 times the limit as x approaches 5 of x, you can just plug in that 5. It's just a 5. Plus, what did we say the limit of a constant was yesterday? Back to your rules. The limit as x approaches a of a constant is the constant. So this is just 4. When you plug in that number, the limit goes away. We have evaluated for you. So that's gone. So now we just work this out. 5 squared is 25 times 2 is 50 minus 15 plus 4. And we get 30. So we did that instead of making 2 big tables and plugging in all these values. B. If I want to use my limit laws, we had a limit law that said you can do the top and the bottom separately. So I can do the limit of the top divided by the limit of the bottom. But then, on the top, we can do it like we did the last one. If I have the limit of things added and subtracted, we can just do the limit of each one. So the limit as x approaches negative 2 of x cubed, plus, I can put that 2 out in front, 2 times the limit as x approaches negative 2 of x squared, minus the limit as x approaches negative 2 of 1, divided by the limit as x approaches negative 2 of 5, minus 3 times the limit as x approaches negative 2 of x. I had to write that limit 5 times for this limit law. Now we can use the laws to evaluate each of these. So the limit as x approaches -2 of x cubed, what's that turn into? Plus 2. What's the limit as x approaches -2 of x squared?
-2 squared.
What's the limit as x approaches -2 of 1?
Just 3.
If it's a constant, the limit doesn't change it. Limit as x approaches -2 of 5. Limit as x approaches -2 of x. So we get -h plus -2 squared is 4 times 2 is 8. And I get -1 over 11. Okay, this is not just approximating from a table. Okay, this is the true value of the limit, the exact value, no rounding error or anything. So I used my limit laws, but what did I ultimately just end up doing? Plugging in, didn't I? All I really did on the first one, I plugged in a 5 for all my x's. On the second one, I plugged in a -2 for all my x's. Isn't that annoying if this whole time I've been making it do all those tables and really all you had to do was plug it in? So sometimes you can just plug it in, sometimes you can't. As long as you can plug it in and you get an answer, so you're not getting something divided by 0, you're not getting an undefined, it is actually legal to just replace that. So that's the direct substitution property. If you have a polynomial or a rational function, so a polynomial or the division of polynomials, you can just plug in your number as long as it's in the domain, so as long as it's not going to make our problem undefined. So let's look at this one. So could I just plug it in on this one? What happens if I plug it in? You get 0 divided by 0. So we can't just plug it in. Is there anything you could do with x squared minus 1 and x divided by x minus 1? Is there any way we could reduce that?
Take an x.
How does x squared minus 1 factor?
Oh,
X plus 1, x minus 1.
And then what happens? We cancel those x minus 1, so all we now have is the limit as x approaches 1 of x plus 1. So now can we plug it in? Yeah. Let's put it in, so it's 1 plus 1, which is 2. So if you're getting something that doesn't work out when you try to plug it in, you might need to reduce first. So that's all the next box tells you. We can reduce and simplify our functions beforehand so that we are able to plug things in. All right, let's talk about a piecewise function. So I want the limit as x approaches 1 of g of x. And g is this piecewise function. X plus 1 if x doesn't equal 1, and pi if x does equal 1. All right, if I just plug 1 into this function, which piece would you be on? The top or the bottom, if x equals 1? The bottom, and you would get pi for your answer. right? That is actually not the value of this limit. Because the idea of a limit, we don't care what happens at the point, we care what happens as you get close to the point. So if you are just getting close to 1, which of these pieces would you be using? The top one. Can you plug a 1 into there? So you would just get 1 plus 1, which is 2. Graphically, what this says, this is a line, y-intercept of 1, slope of 1. Since it's when x does not equal 1, that's an open circle on the graph. Everywhere else is closed. When x does equal 1, you get out pi, so that's like a closed circle. So we can see from this graph as well, it's approaching 2 right there. So if we have a piecewise function, we have to think about it. I don't care what happens at 1, just as I'm getting close to it. So if I'm getting close to it, I'm on that first piece, and we can plug in and evaluate that. What do you guys think you would need to do here? Can we just plug in from the beginning? Okay. Why don't you guys start multiplying this out and see if you can get to the point where you can plug it in. So I want you to start getting in this habit. Until you actually plug in your 0, I want you to write the limit as h approaches 0. So on the top, 3 plus h squared, you have to write that twice and FOIL it, so you get 9 plus 6h plus h squared. And so then what happens? You guys have been working this out? Yes, the 9's cross off. So we're left with 6h plus h squared divided by h. So I'm still writing my limit as h approaches 0. So we have 6 plus h remaining. At this point, can I plug in 0 and get an answer? Yes. So when you plug it in, that's when the limit goes away. So my final answer is 6. But you have to write that limit on every step up until that. Is this easier than making tables of values and graphing and all that? And we're getting the exact answer, not guessing at our answer. Let's look at this one. Can I just plug in my 0 here? No. Can I multiply things out like I did on the last one? No. Do you have any other ideas?
Take it out of the square root.
Okay. I would like to get this out of the square root so I can cancel some things. But if you have things added, can you just cancel the square root? So what have we done in the past when we had radicals on the bottom and we need to get the radical off? We needed to get it square, so we had to multiply by something. Remember multiplying by the conjugate to get that radical off the bottom? So we are going to multiply top and bottom by the conjugate, which is the same thing, but you change the sign. So it's the square root of t squared plus 9 plus 3. And I'm going to do that on the top and the bottom. So I haven't evaluated my limit, I have to keep writing it. On the top, when you multiply those, square root of t squared plus 9 times the square root of t squared plus 9 just gives you t squared plus 9. Because they're conjugates, outside and inside cancel, minus 3 times 3 is 9. On the bottom, I am not going to distribute because I'm hoping that t squared is going to cancel out in a moment. Because that's the thing that's keeping me from plugging in anyway. So t squared plus 9 and minus 9, those 9's would cancel. And then what happens? T squareds cancel, so that just leaves us with a 1 on top. Square root of 2 squared plus 9 plus 3. Now can I plug in my 0? Yeah, it's no longer giving me 0 on the bottom, so we can plug it in so the limit goes away. So 1 over square root of 9 is 3 plus 3. So we get 1/6 for this limit. So far, so good. So one thing we talked about when we looked at graphs is if this limit exists, that means the left and right hand have to go to the same thing. So in general, if you have the limit as x approaches a, if that's going to equal a number, then as you approach from the left and the right, it also has to equal that number. So I just want to look at a few more examples, and then we'll probably stop for today. We're not going to finish our notes today. So I want to show, I'm already telling you, this limit does equal 0. I want to prove why that's true. I don't have a limit law that says you can just plug it in if it's inside an absolute value. So that's why I can't just put it in there. We don't have a limit law that says that's okay. When we have an absolute value, what does absolute value do to a number? It makes it positive. So if you plug in a positive number, does it change it? So the absolute value of x is just equal to x if your x is already positive. And if you put in a negative, it turns it positive, so it's the opposite of x if your x is negative. This whole year, guys, anytime we see an absolute value, we are going to rewrite it using this piecewise. I think this is already the second time we've done it. We did it one time already. None of our calculus rules apply with absolute values, so we have to rewrite it so it's not. So let's do the left and the right hand limits. So I want to do the limit as you approach 0 from the left of our function, and the limit as you approach 0 from the right of our function. If you are approaching 0 from the left, that means you are plugging in things smaller than 0. So which of these steps are you on, the first or the second? The second. If your x is smaller than 0, then our function is a negative x. Now, can we just plug a 0 in there? That's just a polynomial. It's just like a -1 times x. So we can. So -1 times 0 to the left, you're still approaching 0. And we get 0. If you're approaching 0 from the right, you are plugging in things bigger than 0. So which piece are you on, top or the bottom? The top. So my function is just x. Now when we're plugging in, if it's from the left or the right, when you go to actually plug in the number, you ignore that left or right. So the left or right told me which piece I was on. But ultimately here I'm just approaching 0. So if you plug in 0, you just get 0. So these things are equal. So overall, the limit as you approach to 0 is also 0. Okay, we could have got that from a graph too, if you think about the absolute value. Those pieces meet there, so it all works out. But here we did it using our limit laws. Questions? Let's look at this. So I'm already telling you, this limit doesn't exist. I want to see why. So we could use a graph to do that, but we could also do it like we did the previous example. If you take this function, that's the value of x divided by x. Can you plug 0 in here at all? So we're just going to have one case if x is greater than 0, one case if x is less than 0. You can't actually equal 0 in this scenario. So if you plug in a positive, the absolute value of a positive number is that number. So x divided by x would be 1. If you plug in a negative number, the absolute value of that negative number would be the positive. Divided by the negative, you get negative 1. So if we look at the left and the right hand limits, if you're approaching from the left, you are plugging in things smaller than 0. So which step are you on? The top or the bottom? The bottom. If x's are smaller than 0, we're on the bottom one. So it's just negative 1, and the limit of a constant is the constant. So this is just negative 1. If you're plugging in things bigger than 0, then we are on the top. So you have the limit of positive 1, which is 1. These are different numbers. So the left and right limits are different. So that means the overall limit at 0 does not exist. The left and right have to be the same for it to exist. I want to stop here today. There is a handout posted on Classroom, and you've got the rest of the hour to work on that. Please practice using good notation. So